In this lesson, we will talk about the diffraction of light and how it is interpreted in terms of waves. Diffraction is the bending of waves when they encounter an obstacle. You can find an excellent video demonstrating diffraction of light through a single slit by searching the MIT OpenCourseware channel on YouTube. Here are some snapshots from the video. In the demonstration, a red laser beam with a wavelength of 632.8 nanometers is passed through a slit. Here's the slit. Here's the laser beam going through the slit. The size of the slit is adjustable. We can make the slit wider or narrower by turning the screw here. The light that passes through the slit is observed on a screen behind the slit. Here's the laser beam passing through the slit, and here's the screen. And here's where the laser beam hits the screen. What do we expect to see on the screen if light is made up of a stream of particles? If light were made up of particles, we would expect to see just one spot on the screen. We expect that spot to resemble the slit. In other words, the narrower the slit, we expect that one spot to be narrower as well. But what are the actual observations? If the slit is narrow enough, we actually see more than one spot. What's even more surprising is that the narrower we make the slit, the wider the spots become. These observations can only be explained if we think of light as being made up of waves. Here's how. The spreading of light on the screen is due to diffraction or bending of waves. But why do we see bright and dark spots instead of just one spot that monotonically diminishes in brightness as you move away from the center? A location on the screen is bright if the light waves hitting that location are in sync. We say that there is constructive interference of the waves. This illustration should help you visualize constructive interference. Let's examine the two waves drawn here. You will notice that the crests occur at the same location. Here are the crests of wave 1, and here are the crests of wave 2. Therefore, we expect the crests in the resulting wave to be at the same locations as well. Here, the amplitudes of wave 1 and wave 2 are shown to be x, because the waves are constructively interfering. We expect the amplitude of the resulting wave to be 2x. Similarly, we can say that the troughs of both waves also occur at the same locations. Here are the troughs of wave 1, and here are the troughs of wave 2. Because the waves are constructively interfering, we can say that the troughs in the resulting wave also occur at the same locations. What about the dark spots? We say that the waves hitting these locations have destructive interference. In other words, they cancel each other out. Here's an illustration of destructive interference of two waves. Here are the crests of wave 1. You will notice that they occur at locations where the troughs of wave 2 occur. At these locations, the waves add up to 0. We can also see that the troughs of wave 1 occur at the same location as the crests of wave 2. This is true for all locations. Wave 1 and wave 2 add up to 0 everywhere. You could say that with destructive interference, we have a case of light plus light equals darkness. Recall that EM waves are sinusoidal functions of location and time. How can we relate constructive and destructive interference to these functions? Consider two EM waves that are propagating in the positive x direction. If both have the same amplitude, wavelength, and frequency, they just differ in their phase angle, phi. Constructive interference occurs between the two waves if their phase angles are the same. We say that they are in phase. We get destructive interference when their phase angles differ by pi or 180 degrees. We say that they are 180 degrees out of phase. Recall that a change of 2 pi in the argument for the sine function constitutes one cycle, so pi constitutes half a cycle. In other words, we get 100% destructive interference when one wave is half a cycle ahead or behind the other wave. We can say that they are 1/2 wavelength out of phase. The light emerging from the slit is brightest in the middle of the center spot because all the waves hitting that spot are in sync. We say that there is 100% constructive interference of all the waves hitting that location. At the other locations, the light we see are due to bent waves. These locations are less bright due to partial destructive interference. In the darkest locations, such as this one, there is 100% destructive interference. Where do these occur? If W is width of the slit and theta is the angle of the bend to get to a dark location, W times sine of theta is equal to a multiple of lambda. Lambda, 2 times lambda, or 3 times lambda, etc., etc. Here, lambda is the wavelength of the light. It can be shown that W times sine of theta is equal to lambda at the first minima, at this location and this location. And W times sine of theta is equal to 2 lambda at second minima at this location and this location. In general, for the nth minima, W times sine of theta will be equal to n times lambda. Consider two waves emerging at point A and B in a slit that has a width of W as illustrated in this diagram. Let's consider the case where points A and B are separated by a distance of W over 2, which is half of the slit width. And let's examine the wave from points A and B that are bent at an angle theta. If angle BCA as shown in the diagram is a right angle, then it should be easy to show that angle BAC is congruent to angle theta, and therefore sine of theta is equal to the length BC divided by W over 2. The wave from point B will need to travel an extra distance equal to the length BC before it interferes with the wave from point A. If length BC is equal to lambda over 2, then the waves will destructively interfere when W times sine of theta equals lambda. This corresponds to the first minima. Why? Because for every wave from the top half of the slit, there is a wave from the bottom half that will destructively interfere with it. How about the second minima? If length BC is equal to lambda, then for every wave emerging from the top quarter, there will be a wave emerging from the second top quarter that will destructively interfere with it. Likewise, for every wave emerging from the third quarter, there will be a corresponding wave in the bottom quarter that will interfere with it. It can be easily shown that, for the second minima, W times sine of theta will be equal to 2 times lambda. Consider the single slit diffraction pictured here. Suppose the distance of the slit from the screen is 200 centimeters, and the distance between the first minima is 2.00 centimeters. Let's call it y. If the wavelength of the light, lambda, is known to be 632.8 nanometers, calculate the slit width, W. First of all, the line from the slit to one of the first minima is the hypotenuse of the right triangle, and the angle between it and the line from the slit perpendicular to the screen is theta. From the Pythagorean theorem, we can calculate the length of the hypotenuse to be the square root of the sum of d squared and the square of y over 2. Therefore, sine of theta equals y over 2 divided by the square root of d squared plus y over 2 squared. For the first minima, we know that the slit width, W, times the sine of theta equals lambda. We have enough information to calculate sine theta, and we are given lambda. So we calculate W as lambda divided by sine theta. Here's the calculation of sine theta from D and Y, and here's the calculation of W from lambda and sine theta. Here are the screenshots from a demonstration video from MIT that shows what happens to the diffraction pattern when you put two slits side by side. Here's the diffraction of a 632.8 nanometer laser beam from a single slit with a width of 100 micrometers. And here's one for two slits, same widths, and the slits are spaced 150 micrometers apart. What's the difference, and how can we explain it? It looks like the center band in the single slit pattern is split into 3 smaller spots with the addition of a single slit. We refer to the centermost spot as the zero order spot. The 2 neighboring spots are the first order spots. If the center band were split into more spots, the next spots would be referred to as the second order spots, third order spots, and so on. The letter N or M is typically used to refer to the spots by number. We can refer to the zero order spot as M equals 0, the first order spots as m equals 1, and so on. So what's responsible for the splitting? We can attribute the splitting to interference between waves from the neighboring slits. Here's a graphical representation of the effect of putting two slits side by side. In this particular case, the diffraction that would be due to just one slit is given by the blue curve. If we were to predict the interference pattern from one wave from each of the slits, then we would get the purple curve. Here are the peaks in the two slit interference responsible for the first order spots, and here are the peaks responsible for the second order spots. Multiplying the blue curve and the purple curve gives us the red curve. The splitting of the central band depends on the separation of the slits. In this particular case, the central band is split into 5 spots. The derivation for the location of the peaks in the interference pattern for double slit diffraction is very similar to the derivation for the single slit minima. If d is the distance between the slits, indicated as points A and B in the diagram shown here, there will be constructive interference between waves emerging at angle theta from slits A and B if the extra distance that the wave from slit B needs to travel is an integer multiple of lambda. We can write BC equals m times lambda, where m is an integer. It's easy to see that BC is equal to d times sine of theta. Therefore, the location of the mth order peaks are such that d times sine theta equals m times lambda. We can create what's called a diffraction grading by carving, using a sharp tool, a very large number of precisely positioned parallel lines on a piece of glass. The regions between the lines will serve as slits. Photographic replicas that look like plain clear plastic in a cardboard frame, like the one shown in this picture, are available commercially and are quite inexpensive. Gratings that have two sets of mutually perpendicular lines are also popularly sold as rainbow glasses. Here, light from a red laser pointer is passed through a diffraction grating, and the zero order spot, labeled B, and first order spots, labeled A and C, can be seen on the whiteboard. The locations of the mth order spots relative to the zero order spot are given by the same equation we got for the two slit experiment. D times sine theta equals m times lambda. Here, lowercase d is the distance between adjacent lines. Diffraction gratings are usually labeled with the number of lines per millimeter, so d in millimeters is just the reciprocal of this number. Using a diffraction grating with a known d and measuring pertinent distances, we can calculate the wavelength. For m equals 1, the wavelength is equal to d times y1 over the square root of big D squared plus y1 squared. Here, y1 is the distance of the first order spot, labeled A or C in the picture, from the zero order spot, which is labeled B in the picture. So y1 is either distance AB or BC. These should be the same if the laser beam is perpendicular to both the diffraction grating and the wall. Big D is the perpendicular distance of the grating and the wall. So this triangle is a right triangle, and y1 over square root of d squared plus y1 squared is just the sine of theta. If we want to be sure about the value of lowercase d for the grating, we can determine it by using a laser with a known wavelength.